Right. So our talk, ours titled Papers, Please. So before we get started, anybody in the room know the game Papers, Please? Just raise your hands. So not a lot, actually. I'm surprised. Okay. So Papers, Please is basically it's a fictional country where you are like an immigration officer and you're checking people. You're checking their papers, right? So checking their passports and making sure that it's signed properly, it contains all the valid information, and so forth. So that's kind of where we got the inspiration for the title. So a quick background on myself. I'm one of the co-founders at Kusari, a supply chain security company. I'm also an open source maintainer on the project GUAC, which is a graph for understanding artifact composition. We'll talk about that in the coming slides. Also Fresca, and then in Toto attestations, which Salsa attestations and so forth are kind of built on, and then in Toto Golang.
Hello, I'm Mihai Maruseac, or Taylor Swift, it's Mihai. And I'm a member of Google Open Source Security team and also co-chairing for AI OpenSSF AI working group and a member of the Haskell security response team. So I'll take advantage of the talk that Samuel made about adding SigStore for Haskell, and I'll probably do that in the next year. And open source maintainer for TensorFlow, Legacy, GUAC, that's why I'm here. Model transparency, it's the AI supply chain security, and Hindent is from Haskell. So. Oh, sorry, it's still me. Okay, so let me put on an attacker hat, and let's say I want to infect some users with AI, because AI is all the hype, and I want to be malicious. So I'm going to build some models that are malicious. One of them can contain malware, and the other one is a GPT model, is a chat model, but trained on unsavory text. And I want to get these models to the users. I cannot just tell the users download the model from here. I actually have to first upload the model to a model hub. And when I do this, I have to give the model some description into the model card. And now I wait for the users to search for a model that matches what is in the model card, and then the user would download it. Of course, the users are not going to check just the model card description. They're also going to look at the model name. So if they see a model that says it's a malware detection model, but the name is evil model, probably they're not going to download it. But that is a problem that I can easily solve. I can just rename the model. And now nobody wouldn't be wiser. They will just download the model. They will get infected with malware. They will chat with 4chan and so on. So by themselves, the models are not attributable to the user who trained them. Looking at the model card, you cannot know what was into the model, what data has been used to train the model, because in the end, the model card is just some description that the human writes, and it's not verified, it's not tamper-evident, tamper-proof, and so on. So that's something that we want to solve. And this is not just something theoretical. Just a few weeks ago, a ByteDance intern was found out to sabotage another intern just to get ahead. They would inject malware into checkpoints or modify the weights. They would kill the training process such that the other intern would start training a model with tampered weights, and the end result would be bad. And in the end, they got fired, but it cost ByteDance several $1 billion in the process. So we want to prevent this. Okay, so now removing the malware, removing the malicious hat, let's think about how models are trained. In general, you start with datasets. You get the data from the internet, maybe multiple sources, and now you have to adapt them. Maybe in one dataset, the columns are all numbers between 0 and 1, and in the other ones are numbers between 0 and 200. So you need to rescale them. Or maybe you have missing data, or other processes where you want to combine the data, to operate on the data to generate a cleaner dataset. So we have all of this loop where you operate on a dataset. At some point, you have data that is acceptable for your model. So now you pick a training framework, TensorFlow or PyTorch. You decide on a model architecture, maybe how many layers, transformers, and so on. You write some code for that, and now you train the model on the data with the code that you write. Once this model is trained, you deploy it somewhere to the model hub, and now you wait for this to come into production. It's not that simple because larger models, large language models, and so on, they don't go via one single round of training. In general, you take the model from the model hub and you train again on new data set. This is, for example, the scenario with fine-tuning. You take a model that is trained on general use cases, and then you fine-tune it to perform better on specific scenarios. Or you can take a model from the model hub, and you might transform it to fit the application. So for example, if you want your model to work on mobile applications, you quantize it. You transform all the weights to integers. That's another training loop. At some point, you have a model that you are ready to deploy into your application, and you cannot just serve the model itself. You have to embed it into an application. So now you have your application that you can serve to users. And of course, this starts to look very similar to the SLSA supply chain level diagram, and it has similar risks. You can have data poisoning. All the data processes can inject malicious data that then will impact the downside model. Or you can even have model poisoning. You have the model in the model hub, and somebody that has write access to the model hub might modify the weights to make the model misbehave. Or even compromise the model storage. Having access to the model hub, having write access, I can inject malware into the model. So now when you load your model into your application, besides having the model, there will also be some malware that runs there. Or I can trick users to use bad models into their application, and so on. So there are a lot of supply chain risks that we want to solve. And the best step to starting to solve this, the first step is to sign all of the outputs and verify them before we use them further into the process. So in this case, we can sign models that get trained and dataset that gets produced with Sigstore and verify them across the chain. We have a proof of concept for signing models with Sigstore, and we're going to operate further into integrating this for both for models and datasets. And how does it work for models? We have the model trainer, the model training pipeline. As part of the training process, at some point, it will connect to the Sigstore certificate authority with the identity of the workload, and will receive back a certificate that is valid for a short amount of time, exactly as Sigstore works. This certificate can be used to sign the model, and we put the signing event into the transparency log, into the Sigstore transparency log, and we get back the log inclusion proof. And now when we upload the model to the model hub, we are going to upload the model, but we're also going to upload the certificate and the inclusion proof. Basically, we upload the Sigstore bundle associated with the model. Now, the model hub itself can verify the signature, or for some cases where, let's say, you already started training the pipeline and you discover that you couldn't have signed the model at the end, you might still have a chance to sign the model as you upload it to the model hub. And then the users can verify the model when they download it from the model hub, or they can just trust the model hub. We have written a small library for model signing where we have various approaches for hashing the model bits and signing the model. And the QR code here points to a demo notebook, a Colab notebook, that downloads a model from Hugging Face instead of training it, so simplifies the amount of time, and then signs it, tampers with it, verifies the signature, and so on. In the interest of time, I want to stop here for the QR code, but we'll go on to the next step. So let's say now we have signing for models, for artifacts, but we want to actually get more information because the signature only protects the bits against tampering, but we also want to record who is the person that trained the model, on what data set the model has been trained, what process has been used to build it. And this is where SLSA comes in, and I'll let Parth.
Awesome. Yeah, so signing gets us a part way there, right? So we need to go further and use SAL statisticians. I think a lot of people in the room are probably familiar with what SAL statisticians are, but just a quick recap, right? A SAL statistician is going to give you an understanding of how exactly, how was it actually built? And how was, in this case, is usually with software artifacts, but like how was the software artifact or the AI model built? Where was it built from? And then what kind of materials and everything that was used to build it kind of come into play. So we want to take the same kind of concept and apply it to AI models. So you can see here, you can see this PyTorch model. We created a SAL statistician for it, and right, it has a specific digest associated with the actual model, which is great. So that's our subject. We have our builder. We're building it on GitHub. So you can see the SLSA framework. We have a GitHub action that's building it. And then we look at the materials. So now we see missing information in the materials section, right? So right away we see it's all that's giving us is the URI of the GitHub repo that it's actually being built from, but no other information. There was no other information about the data sets, what other models were trained on it, and so forth, right? So right, we have the proper subject specification, but for completeness, right, we're missing what data sets were a part of it, the materials, what other models were trained on top of it, and then what frameworks were used, right? So it could be multiple data sets, it could be a lot of recursive nature of how the model is trained, so we're missing all that kind of information. And then on top of that, right now we have a GitHub action, but we do want to go beyond that and have other more secured ML trainers, and then at the same time we want to give this to the developers, right? Make it easy for the developers to create SLSA attestations, right? So integrate this with Jupyter as well as the collab, so that these attestations can be generated automatically as they're kind of in their workflow. So there's three. So we talked about, Mihai talked about model cards, right? That focuses on the ML. It talks about the data sets and licenses, but it's human produced. So we want to generate, SLSA attestations for this that will be machine generated, that will give us this information about the build as well as all the inputs that kind of went into it. And then from there we can and then taking all this information, we can create an AI bomb out of that at the end of the day. That gives us all the dependencies and all the things that kind of went into it.
Okay, so looking back at the diagram, at the supply chain diagram, the other thing that comes to mind is dependencies. We have a model that has been trained from different other models with different data sets, with the TensorFlow or PyTorch ML framework, which also come with their own dependencies and so on. And of course, we can generate SLSA provenances for every step into the supply chain, but we have to somehow merge all of this information together. And we'll see how to do that in 2 slides from now. But first, let's look more into details at the dependencies concept. So in traditional software, so software that doesn't use AI, the dependency tree has kind of like this shape in general. You have one package that has a lot of direct dependencies, and then they have like a few subset, and at some point the tree stops. So the tree is very wide, but also very narrow. This is, for most cases, there are corner cases where you can have hundreds and thousands of dependencies, but in general, this is like the shape. Whereas if you look at ML, the tree is narrower, so one model is trained from one data set and maybe fine-tuned from another model, and that model, again, has only 1 or 2 dependencies and so on. But the tree is also deeper, because each time you iterate on a data set, you basically create another level into the tree. Each time you quantize a model or you distill a model and so on, you create another level into the tree. So in this graph, I'm actually showing 2 separate dependency trees for several models. The yellow one is what researchers do when they have a new idea. They have a small data set. They want to train a small model on that just to test their idea to see if it works or not. Once they see that the idea works, then they move to some other data set. They might rescale it, reshape it, and make it work. So that's going from D1 to D2. Or they might train a model. Once the model is trained, maybe they want to train a more tuned model for a specific use case, so they do fine-tuning. And then at some point, they want to convert this model to some model that goes into the application. So for example, checkpoint model to a saved model format for TensorFlow that you can directly deploy into your application and serve it directly to users, and so on. So this is what, imagine now that for every step into this diagram, you have a SLSA provenance that is complete, that records both the inputs and both the outputs. So what we generated was exactly this diagram with these 4 data sets and 6 models. We generated SLSA diagrams for everything. We wrote another script that makes sure that the SLSA diagrams are all complete, re-signed everything with SIGSTOR, and now we started analyzing the supply chain for these models using the next tool.
All right, so quick recap, right? So we're using the SIGSTOR at the bottom, so we're using that for signing, right? We have the software attestations, which is going to be our SLSA as well as the SIGSTOR. And then next layer above that is now all of these software attestations are usually JSON, right? Or JSON lines and so forth. So what do you do with this information? Can we take this information, right? They're all separate documents, so that's not really helpful. We want to take all this information, decompose it, and then use it all together. So that's where GUAC, or Graph for Understanding Artifact Composition, comes in. It's taking all this information, decomposing it, and then dropping all this information into a graph database so that you can create all the relationships out of it. And then from there, we can use it for policies, and we can use it for insights and whatever else we want to use it for, right? So if there are specific, and we'll talk about this, so a specific data set, for example, may have been tampered with and so forth, how do I know exactly where, which model was trained on it? right? So now I don't want to be, you don't want to be sitting there looking at the JSON documents yourself. You want to have you can query the graph and get the answer right away about what depends on it and what it was used by. And we'll show that off in the coming demo. So just a quick overview of what GUAC is, right? So GUAC is started off as, we wanted to make it very modular and very pluggable. So it takes in a lot of different document types. So for example, it takes in, SBOMs, software bill of materials like XPDX, Cyclone DX. Takes in vulnerability information in toto attestations like SLSA, and it takes all this information and it tries to pull in other public data sets. So for example, vulnerabilities, deps.dev information, whatever else out there, right? License information, and then like end of life and so forth, right? It takes all this information in, decomposes everything, puts it into a graph database so that it makes it a lot easier for you to create the relationships and then query for the information that you need, right? So then you can use it, like I was saying, for policies, for patch planning, and then, if anything, if, let's say, something critical happens in your environment, how do you quickly find out where it is, right? So let's jump into the demo. So I'm going to switch over here. So the first thing I'm going to do is I already have GUAC up and running. So yes. Yeah, so I'm just going to ingest some documents. So here, I'm going to go back here. So I just have the environment running. So what I'm going to do is we've already collected all the provenances like Mihai spoke about. They've all been signed by Sigstore. So they're all Sigstore bundles. So we're going to ingest all this information into GUAC, and it's going to decompose and drop it all into the graph database. So this should happen relatively quickly. And then before, just really quick, I want to show off here, if I scroll up. So you can see right here, verified signature against the transparency log. So as these documents are going into the graph database, they're all being verified via the Sigstore bundle. So you can, so they haven't been tampered with, and you know that they're valid. And because there were 10 documents, all of these you'll see disappearing 10 times, multiple times, because they were all validated against each other. Right, they were all separate documents. So now, because the way this also was defined and how GUAC works is going to take all this information and create nodes and relationships out of it, right? So now all these 10 documents that were separate now became a graph of all interconnected information. So now we can query on some of this information. So the first thing we're going to look at is that simple model that Mihai talked about initially that was just trained on one data set. So I'm just going to use that. I'm going to query it based on the subject digest that was there, and it's going to pull up, okay, so what information, all the different SLSA information, what materials that were within it, and then recursively going down all the different SLSA attestations that were part of it, and the data sets and so forth. So you can see right here is our actual model, and then you can see all the different materials. And I've truncated the hashes here so that it's easier to see. But the different materials that were used, this is the different data sets. So if I search for a specific one, for example, so if I search for this one, and you can see down here, there is a specific SLSA attestation for it, and then you'll see what materials were if it had more materials that it was trained on or whatever else, it would appear at here. In this case, it's only showing us the SHA-1, which is going to be the repo that it actually came from. And then we can quickly visualize this. So I'm going to take this and let's see, switch back over here. Is that the right one?
Yeah, it's the right one.
Okay, good. Yeah, so let me zoom in a little bit. And it becomes a little bit of a jumbled mess. So we're still trying to work on a good way of outputting some of this information. So you can see right away this is our actual model that we started with, and this is the digest of the actual model. And then you can see the different SLSA attestations. So this is all the materials that it got trained on. So you can see how it broke all the information out and then ingested everything into the graph. And then you see here they're all pointing to this SLSA framework, GitHub Action, which is what they were built from, and so forth. So the next one we're going to look at is the fine-tuned model. And Mihai, if you want to.
Yeah, so this one is an example of a model that has as dependencies both other models and other data sets. And the model that has a dependency was also built from other data sets. So now we should see a larger graph with more dependencies, more data sets showing in, and also models as dependencies.
Right. So right away you see, so if I scroll down here, this is the specific digest here. So if I search for it, we can see that it's part of the materials of our fine-tuned model, and then it contains other materials that it was built from, and so on and so forth. So if I keep querying down, it's going to give us a complete a graph of how it was all built out. So And then, like Mihai was saying, we can take a look at this. And again, it's going to be big. Hopefully it's not going to be too crazy. There we go. And come on, zoom in. Yeah, and then you can see our model is down here, which is where it started from. And you can see that this is the SLSA attestation that it started with. And then you can see the material, the different materials that are part of it. It contains SLSA attestations, and then they are linked to other SLSA attestations, which they're linked to other things which contain other materials that are part of it, and so forth. So we're still working on how to, this information is very complicated, right? So how do you visualize this? How do you display this information in a usable form? But at the same time, right, this is just, visualizing it is one thing. You want to take this information and use it as a policy, right? So it's not about looking at the information. You want to be able to make decisions around it. So the policy aspect of it is more important. That's what we kind of focused on.
I mean, even already looking at this graph, you can see that there are two clusters of SLSA pool nodes. That is because one model has a dependency of another model who has a dependency on another data set, and each one of those gives you one SLSA cluster.
Right. All right, and one more example. This is the saved model.
So this is the model that we deploy into the application. It is the final model which has gone through several iterations of data sets, several iterations of model transformations, fine-tuning, and so on.
Yep, and again, the same kind of information kind of shows up. You can see, multiple layers down, the data sets as well as a fine-tuned model, and so forth. So again, one more time, we'll take a look at it real quick. So we'll copy this and drop it into our visualizer. And yeah, you can see it's very complicated and contains a lot of information. So the last thing we want to show off here.
Going from the GUAC output for this model, because this is the model that we deploy into the application, we can also generate an AI BOM by just parsing the table that GUAC responds and outputting it into a JSON format for the AI BOM.
Right. Yeah, so from here we can take this information, via CLI or an API, and then create an AI BOM out of this at the end of the day. So the last thing we wanted to show off was the concept of the data set being poisoned, for example, right? So GUAC has the ability to mark specific artifacts as bad, so we can mark the specific the data set that it was trained on as bad. So that's what I'm going to do here. So it's going to run through. So I'm going to copy this in. And you can see what I'm certifying at the bottom is, based on a regulation, we should not be using this data set, and I'm providing it the hash of the actual data set there. So once that gets registered into the graph database, then I can query for that specific object that's certified bad. And what that's going to give me back is basically all the different interconnected nodes that are part of it. So it's going to be like, okay, what was trained on this data set? And then it's going to give me a graph of like, okay, this is all the information that it was trained on. Or I'm sorry, the model that uses that data set. And this can be created into an output. This can be used as in a policy engine, for example. So in future use cases where, let's say, the data set was used and you don't want it to be pushed to a specific, it shouldn't be used in a production type use case. It can be blocked and so forth. So and here we can see the certified bad node down here. So that's our data set that is bad, and we can see the arrows kind of pointing in. So that's where that it's a material for this particular model is using that data set and so forth. You can see it all the way cascading downwards. Anything else?
Yeah, so we can use this, for example, if you detect that some images in your data set are invalid, you can just mark as bad the hash that contains those images, and then it will transitively mark as bad everything that was trained on those images. And also you can use it on the integration side. So suppose you have your model and you want to build an application around it. As soon as you pull the model from storage, if you integrate with GUAC, GUAC can raise an alert saying, this model has been detected to be trained on some data set that since then has been proven to be invalid. You should not train this model. You should not be using this model into your production. You should not be training upon this model and so on, unless maybe you get some approval and so on.
All right, so we just want to say, everyone in the room, thank you for being here. You're all the best. but also SLSA, Sigstore, and GUAC are also the best. And we also have a happy hour tonight, so if you guys, if you wanted to talk more about this, Mihai and I will both be there, so be sure to stop by. So happy to take questions. Thank you.
What, if any, signing formats do model hubs support today?
0. So right now it's 0 formats, except Hugging Face signs the commit with GPG. So the commit when you add a model, it's signed with GPG. And that kind of works, but we're going to talk with them and integrate model signing with Sigstore into that. So that's on our roadmap for early next year.
So the attestations, the SLSA provenance that is being emitted from your pipelines that you're intending to use to drive policy decisions, what reason do we have to trust that SLSA provenance?
So right now, it's as part of our training pipeline. We are just saying, we know that this model has been trained from this data set, so we merge the provenances together. But in the future, on our roadmap next year, is to actually make the SLSA provenance complete exactly as the GitHub SLSA generator runs on a separate workflow. Right. We want to do the same for detecting materials. So Parth was talking, for example, on certified trainers. A certified SLSA trainer would be one that records all the materials, all the data sets that you're touching, all the models that you're touching, and would record those into the provenance. And for example, when we make a Colab notebook or a Jupyter notebook like this, it should also record the order in which you run the cells. Because maybe you run cell 1 and then cell 10 and then cell 2. That would give you a different model than running the cells in order.